Hello students, welcome to JTS Junior College online teaching learning platform. I am Parag Solanki, your mentor for subject physics, and we are studying chapter 12 electromagnetic induction. Today we are going to study about eddy.
The word eddy literally means a circular current. Let us now try to understand how they are produced. Take a solenoid that has a soft iron core. Now connect this solenoid to an AC source. When a metallic disc is held over the cross-sectional face of the soft iron core, the metallic disc will be thrown into the air. When current flows through the solenoid, magnetic flux linked with the solenoid increases from 0 to finite value. This change in magnetic flux gives rise to induced currents in the disc. The upper face of the soft iron core attains the same polarity as the lower face of the disc. Hence, the disc is repelled by the soft iron core and is thrown up in the air. This experiment shows that when a conductor is kept in a changing magnetic field, currents are induced in the body of the conductor. These are currents that occur in very small loops and are called eddy currents. Foucault discovered eddy currents in 1895. In some cases, the eddy currents may produce undesirable effects. For example, they increase the internal energy and therefore can increase temperature of the material. For this reason, devices like transformers, which are constantly subjected to changing magnetic field, are often laminated or their metallic core is divided into thin sheets. Each of these sheets are insulated from one another. The magnitude of eddy currents is given by I is equal to minus 1 by R into d phi b by dt. The direction of eddy currents is given by the Lenz's law, or Fleming's right-hand rule. Lenz's law states that the direction of induced current is such as to oppose the very cause producing it. Fleming's right-hand rule. Stretch the forefinger, the middle finger, and the thumb of the right hand, such that they are mutually perpendicular to each other. If the forefinger indicates the direction of the magnetic field, the thumb indicates the direction of motion of the conductor, then the middle finger indicates the direction of induced current in the conductor.
Now we will consider another demonstration of eddy currents. Here we are going to take a strip which is pivoted at one end and the other end is allowed to rotate, oscillate through the magnetic field. Let us see what happens when a metallic strip is allowed to oscillate through magnetic field.
I have here a piece of aluminum suspended on a pendulum arm, and I have a powerful magnet, permanent magnet down here. It produces a magnetic field in this direction, and when this piece of aluminum enters that strong magnetic field region between the two poles of the magnet, the change in the flux, the magnetic flux, through this piece of aluminum induces an EMF in the aluminum and currents in the aluminum. And the direction of those can be determined by Lenz's law. If the magnetic field is in this direction, as the aluminum enters the magnetic field region, the magnetic flux is increasing. It's increasing in this direction. To oppose that increase, there are currents that go in this way that produce an induced magnetic field in the direction opposite the original magnetic field. And that works out, those actual currents produce a force that opposes the actual motion of this aluminum plate. So what you'd be looking for is to see that whereas normally this would have oscillated without much friction for a long time, when allowed to pass through the magnetic field, the force is quickly, or the motion is quickly damped out. See that a little bit better. That's called eddy braking. It's used a lot in amusement park rides, actually, to slow down amusement park cars and roller coasters, etc. Now, with this piece of aluminum, we've got slits cut into it. So those circular eddy currents are not, this will prevent any eddy currents to be produced. So this one can oscillate for quite a good long time and be very happy. The other thing to mention about this one, a solid piece of aluminum, is that not only do you get braking as it enters the magnetic field and as the magnetic flux is increasing through it, but you also get braking as it exits the region of the magnetic field, and you get currents in the opposite direction. Both when entering and exiting, it tends to slow it down. So that's eddy braking, and one more example of Faraday's law.